Okay, so last time we began discussing Einstein's special relativity. We began by introducing the postulates of special relativity, and then we moved on to talk about the relativity of simultaneity. So just as a quick rehashing, the first postulate is that the laws of physics are the same or covariant in all inertial systems. That is, that the mathematical form of a physical law is going to remain the same. Our second postulate is that the speed of light in vacuum is a constant, independent of the inertial system, the source, or the observer. We then talked about the relativity of simultaneity. For a refresher on that, I'd recommend taking a look at the last video. For this video, I wanted to start by discussing other consequences of what you guys agreed to last time, which was that we are going to accept that there is a speed of light and look at the consequences thereof. And when Einstein started thinking about this, he recognized he would need a very powerful clock. Um, and he decided to base it on the thing that we would all agree on, the speed of light. And so in this telling of the story, we're going to build Einstein's light clock. This is going to be a thought experiment, and you'll see why in a second. Um, so first, note that uh, Einstein is going to take a light source, let's let it be a flashlight, and put it uh, in the floor. And we'll shine the light directly upwards uh, to a mirror that is positioned some height h above, and then it will reflect back. That will be one tick of the clock. If you're old-fashioned like me, perhaps you want uh, the clock to tick once per second, in which case you would need h to be 1.5 times 10 to the 8 meters, right? Because the travel distance that the light would go through is 2h. It would travel h up and then h back. Since the speed of light is about 300 million meters per second, you need 2h to be about 300 million meters in order for the clock to tick once per second. That's why this has to be a thought experiment, right? This isn't a clock you can build in your living room. So Einstein builds this clock in his head and uh, and sees the light travel straight up and then straight back down, and sees that he is happy that the clock ticks once per second. Through this series of mirrors, it keeps doing that. He's very proud of this clock, and so he wants to take it on tour. And so he puts it in the fast mode of transportation of the day on a train. If Einstein is going to charge uh, $1 to see this clock, well, I'm too cheap to pay for that, right? Do you know how many Milky Ways I could have bought in 1905 with $1? 0. They didn't have Milky Ways, so terrible time. But the train is going to travel along the tracks with some speed v. I may be too cheap to pay to see the clock, but I'm not too cheap to stand along the side of the road and watch the train go by. Note that Einstein says that the time for one tick of the clock, the time elapsed, delta t sub e for Einstein, is just going to be 2h over c. Hopefully you'll convince yourself of that This is just kind of a rehashing of our statement that the average speed is distance covered over time spent, and rearranging to solve for delta t. So let's look what happens from my perspective. Well, from my perspective, I see the light leave the flashlight, and I have to agree with Einstein as to what happens. It bounces off of the mirror above it, and then it also comes back to from whence it came, right? But here's the tricky part. Um, in order for that to happen, I have to see the light take a path more like what I've tried to badly sketch here for you. Note that we can draw a pair of right triangles here, and we can sort out uh, how long I think that this path, uh, how long it takes for the light to travel this path by just using Pythagorean theorem. And so what we have is c delta t m, m for Mark, over 2 squared, right? This is just a squared plus b squared is c squared. Maybe I shouldn't use c since I don't want to confuse you with the speed of light, but simple Pythagorean theorem. The hypotenuse, the, the, the path I've drawn in red here, c delta t m over 2, right, is equal to v delta t m over 2. That's how fast, or that's how far the train has traveled sideways in the time it took for the light to go from the floor to the ceiling, plus h squared. That's the vertical leg of this travel, right? And so we could, and I will leave this as an exercise for you, solve that for delta tm. And if we do, we get the following. We get that delta tm is just 2h over c divided by the square root of quantity 1 minus v squared over c squared end quantity. But remember, the numerator there, 2h over c, is just the time interval that Einstein would have predicted for and observed for the travel of the light path. And so notice that the two don't agree. In fact, since uh, v is less than c, note that I'm going to say that Einstein's clock is running slowly. I'm going to yell, hey, Einstein, there's, before you take that clock on the road, there's something wrong with it. It's ticking too slowly. It's not actually ticking once per second. So Einstein will look at his clock and verify that it's still ticking once per second from his vantage point and say, no, my clock is fine. And I'll say, well, I can prove it to you. I'll build a clock of my own. And so let's build a clock of our own. Oh, goodness. All right. So we build a clock of our own that is also going to be h tall. And from Einstein's vantage point, both myself and the clock are moving with the same relative velocity v, at least in magnitude, but in the opposite direction. And so you can probably see that what would happen here is that the same thing is going to happen in reverse. Einstein sees that the path that the light took is greater than the path that I say the light took, and consequently he is going to say that my clock is running slow. So who's right here? Well, your intuition might be to assume that Einstein's right. Einstein was a much better physicist than I am. But the interesting thing of relativity is that in order for us to both agree on the speed of light, we can't agree on the time between these two events. In fact, if two frames are in relative motion to one another, you will see that a person in one frame views the other frame as passing time more slowly. We call this time dilation. This is going to instantly lead to another feature, though, that if our definition of average speed is that speed is equal to distance covered over time spent, well, in order for us to agree on the speed of light, if we aren't agreeing on the time spent here, we also can't agree on the distance covered. And so there is something else that is going to come along for the ride, which is length contraction. And we will describe those next. So as we just saw, when we are performing these calculations in our relativity assignments, we're always going to assume that our measurements are valid. But someone in another frame is entitled to assume that their measurements are valid. So how are we going to establish a crosswalk between their measurements and our measurements in our two different frames that are moving relative to one another? Well, the way that we're going to do this is we are going to use these Lorentz transforms. So here we are going to assume that the relative motion is purely along the x-axis. So between your frame and my frame, we both agree that the motion between us is purely restricted to the x-axis. And we can do this arbitrarily just by agreeing to shift our coordinate axes such that that's true. So we'll have a primed frame and an unprimed frame. And so to convert back and forth between measurements made in the primed frame and the unprimed frame, well, we could say that x prime is just going to equal x minus vt over that square root of 1 minus v squared over c squared. And that y prime is y, z prime is z. This is interesting, right? What we just saw is that we won't necessarily agree on time intervals. And so the time coordinate here, we don't necessarily agree on. So here we'll say that t prime is equal to t minus v over c squared times x, again divided by that square root of 1 minus v squared over c squared. And if you wanted to convert back the other way, note that the difference between the x prime equals and the x equals formula is just swapping out primes for unprimed, and uh, and switching the minus sign to a plus sign. That's what you. Oh goodness, that's what you see here, right? So hopefully that's okay. Um, I do want to point out something really interesting here, because one common theme that we're going to come back to again and again and again is that, remember, we've spent a long time using Galilean and Newtonian physics, and it's worked very well in our lab experiments, right? And so we need, for all of those statements that have previously borne experiment, uh, to still hold true. And one thing I'd like to point out is that if you take C to be very, very, very large, which it is, right? Let's explore what happens. Well, all of a sudden, V over C, if C approaches infinity, V over C starts to look a lot like 0. So 1 minus V squared over C squared really looks a lot like 1. The square root of 1 is 1. And so what you get is x prime is equal to x minus vt, which Galileo would have agreed with. Y prime is y, z prime is z. Note that t prime is t minus v over c squared times x, divided by, again, that 1 minus v squared over c squared under the radical term. But again, if you let c approach infinity, then then v over c squared, usually for any value of v that we have explored in lab thus far, tends to 0, right? And so, and the denominator again tends to 1, and so we get t prime is equal to t, much like Galileo would have told us. And so what we learn from this is that these relativistic oddities, right? It feels odd. We like to think of absolute time measurements, time interval measurements, and absolute uh, length measurements. That where that starts to differ only really shows up when V over C isn't something that we can ignore. So hopefully that's all right. Okay, so I want to introduce uh, the thing that's going to allow us to measure between time intervals and length measurements between two frames at with constant relative velocity between them. And the way that we can do this is we could say that delta t is equal to gamma times delta t proper. This is a little unnerving to me. I don't really like to call it proper time interval. Um, but let me describe what I mean by proper time interval. Proper time interval is the time interval measured between two events that occur at the same location. So you might imagine the case of the train that we were examining a second ago, right? Um, Einstein gets to measure the proper time interval because he sees the two events that start and stop the time interval occur at the same location. He sees the light leave the flashlight and the light return to the flashlight. And it's right at his foot, right? So he sees both the start and stop of the time interval, the events that define that occur at the same location in space. I didn't get to measure a proper time interval there because I don't see the two events occur at the same location in space. I see the light leave the flashlight right here, and then I see the light return to the flashlight over here. And so those are two spatially disparate points. And so I do not measure what we call proper time. Again, using the term proper time interval makes it sound, it's a normative statement, right? It makes it sound like one is correct and one isn't. And again, I want to point out that we're both entitled to our own measurements. So I really don't mean that one is correct and one isn't correct. But looking at this again, we could say that if Einstein measures 1 second as the time interval between the light leaving and the light returning, well, since v is greater than 0 but less than c, v squared over c squared is going to be between 0 and 1, and so 1 minus something like that is going to be some number less than 1, the square root of which will also be less than 1. 1 divided by something less than 1 means that gamma is going to be greater than 1. And so delta t will always be greater than or equal to delta t proper. Hopefully that makes sense. I also want to define what I mean by a proper length measurement. And the proper length measurement is measured by the observer who can see the object being measured at rest with respect to herself. So is measured by the observer that the proper time interval between two events is measured by the observer who sees both events occur at the same point in space. The proper length is measured by the observer who sees the object at rest respect to her. Now, again, coming back to our train here, Einstein sees the train at rest with respect to him. He can measure the proper length of the train. I would not measure the proper length because I see the train moving with respect to me. But for my clock, I can measure its proper length. Note that the proper length divided by gamma is the length measured by the other observer. And since gamma, we said, is greater than or equal to 1, the length measured by me for Einstein's train is going to be shorter than Einstein would measure it. I measure that to be a shorter distance, the length of the train, than Einstein would measure it. Hopefully that's all right. Sorry to tack this back in here, but just to make sure that I've been clear enough in this, going back to the Einstein's clock on Einstein's train traveling past me along the x-axis, I measure Einstein's clock to be passing time more slowly. In other words, I measure the time interval is greater than 1 second if Einstein says that it ticks once per second. And if Einstein says that the train is 100 meters long, well, I would measure the length of the train to be less than 100 meters. Okay, so if we want to measure the speed of an object in my frame, and then have you measure the speed of that same object from your frame, how are we going to agree upon that? Well, let's go back to our Lorentz transforms, where we previously had said that this was true, that x prime is equal to numerator x minus vt over denominator square root of 1 minus v squared over c squared. Y prime is y, z prime is z, t prime is numerator t minus quantity v over c squared and quantity times x divided by denominator square root of 1 minus v squared over c squared. I could think of this in incremental fashion too, though. And in that case, dx prime oh goodness. In that case, dx prime is equal to numerator dx minus v dt over denominator square root of 1 minus v squared over c squared. dy prime is equal to dy, dz prime is equal to dz, and dt prime is equal to numerator dt minus quantity v over c squared and quantity times dx divided by denominator square root of 1 minus v squared over c squared. Now we can simply apply our statement that we've used since physics 130, that the speed is going to go as dx over dt, or in this case, dx prime over dt prime, and that the speed in y is just going to go as dy prime over dt prime, and the speed of along the z-axis is just going to go as dz prime over dt prime. This gives some interesting results, which I'd like to to go over with you. And at this point, I would probably advise that you pause the video, see if you can manipulate dx prime over dt prime, dy prime over dt prime, and dz prime over dt prime to get the following. And since we've already used v for the relative velocities between the primed and the unprimed frames, I'm going to call the speeds u's. And so what we get this time is that ux prime is numerator ux minus v over denominator 1 minus quantity ux times v divided by c squared end quantity, where remember, the relative velocity is assumed to be along the x-axis, and that's true for all of these. Uy prime is equal to uy times numerator square root of 1 minus v squared over c squared divided by denominator 1 minus quantity ux v over c squared end quantity. Where again, remember that the v here is assumed to be the relative velocity along the x-axis. So it is the magnitude of the velocity along the x-axis. And it could be plus or minus. Similarly, uz prime looks a lot like our uy prime, just subbing out z's for y's. But uz prime is equal to uz times the numerator square root of 1 minus v squared over c squared divided by the denominator 1 minus quantity ux v over c squared end quantity. So again, try and manipulate your dx prime over dt prime to get the statement that ux prime is equal to numerator ux minus v over denominator 1 minus quantity ux v over c squared end quantity. And similarly for uy prime and uz prime. Let's try and do an example before we call it for the day. And let's try and sort out, so at the end of this semester, I'm sure that you will all run away from me as fast as possible. And so Natalie and Joey are traveling along the x-axis and the negative y-axis. Natalie has a velocity of 0.75 c, very, very fast, 3/4 the speed of light along the x-axis, as measured by Mark. Joey has a speed of minus 0.9 c along the y-axis, again, as measured by Mark. So according to Mark, Natalie has no speed along z, no speed along y, but she has a speed of 0.75 c along the plus x-axis. Joey, as measured by Mark, has no speed along the x-axis, no speed along the z-axis, but does have a speed of minus 0.9 c along the y-axis. So the question then is, how fast would Natalie see Joey speed away? That's our that is our question here. So we're going to use our velocity transforms from up here. And so I let myself be the unprimed frame. You'll see that this is a recurring theme. I tend to pick myself as the unprimed frame. And so Natalie would be the primed frame traveling with some relative velocity to me of 0.75 c in the x direction. So in this case, what would Natalie measure for Joey in the x and y directions? And so if we plug in the ux is 0, why? Because Mark says that Joey doesn't have an x velocity. Minus v here is the relative speed along the x-axis between Mark and Natalie. Well, that's 0.75 c. Ux again in the denominator is still 0. Mark says that Joey doesn't move along the x-axis. V is still 0.75 c, but 0 times 0.75 c is still 0, over c squared is still 0, and so this becomes 0 minus 0.75 c over 1 minus 0 is just minus 0.75 c. Sorry, you can tell I'm still getting used to this. Similarly, we could figure out what Natalie would measure for Joey's speed along the y-axis. And so if we plug in Mark's measurement of Joey's speed along y of minus 0.9 c over gamma, remember gamma is 1 over the square root of 1 minus v squared over c squared. I'm going to run out of space here. I guess I could call oh no, I can't scroll down yet. Times 1 minus Joey's ux is still 0. V is still 0.75 c, so this is still 1 minus 0. And if we try this, v squared 0.75 is about minus 0.6 when we plug in the values for v. And the value for v again is going to wind up being 0.75 c. Why do I keep doing that? So hopefully that is okay. So now we know what Natalie says Joey's x speed is and what his y speed is. And so if we want to know the overall speed, again, we can just sum and quadrature, right? We can say that that u total prime as measured by Natalie is just equal to what she measured for ux prime squared plus uy prime squared all square rooted. And so if we take minus 0.75c squared and then add it to minus 0.6c squared and then square root, we will ultimately get to I fail. I was trying to highlight that, but I clearly am not going to be able to do so in easy sense. And so we'll get a speed of 0.96c, which is less than c. What we're going to find out is that this will insist that everyone measures every object's speed is less than the speed of light, unless the thing we're talking about is light. Okay, so hopefully this is okay. That sound tells me that it is time to wrap this up. Probably some of you were wishing I'd wrapped this up longer ago, but hopefully you paused this video a few times and stopped for Milky Way candy bars. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow.